Okay class, today we'll look into singular value decomposition at any matrix as U, sigma and V transpose, where sigma is diagonal and U and V is orthogonal, which you know from your past life. If you consider A as a linear operator, or I don't know, you can call it a linear map, or you can call it anything you want, from your row space to column space, and if you have a vector V1 which is mapping into U2? No, it's U1. So you know you can write U1 as AV1. Similarly, if you have another vector V2, you can write it as AV2. Right? You're looking for a particular set of orthogonal vectors in your row space going from V1 to VR. R is the dimension of your range space, right? Which maps into orthogonal vectors in your column space. We can write AV1, AV2 as U1 and U2 and so on. We can write this as, you want to make this vectors as unit vectors. To pull out length of each vector, that is the multiplier that you get. So you get sigma 1, sigma 2, sigma r. You can write the same expression to the full set. For the vectors which are in null space, sigma will be 0 for those corresponding vectors. So you can write it as A V equal to U into sigma, right? And then you can write this. And since V is orthogonal, write this. Now we'll see how you find U and V. You have U as your eigenvectors of A transpose, and V has eigenvectors of A transpose A. That sums up SVD, and we'll look in more detail in today's discussion. Thank you.
How a matrix acts on a unit circle. Assuming that the matrix A is square symmetric and has got real eigenvalues, and it's got the eigenvalue decomposition of the form Q delta Q transpose. Q cos theta minus sin theta and cos theta. I multiply with Q delta, gets rotated by theta in the anticlockwise direction with the delta diagonal matrix that gets mapped into an ellipse. Q is just a transpose of Q transpose. It rotates my ellipse by theta amount in the clockwise direction. Contrast both SVD and eigenvalue decomposition. The only difference is the orthogonal matrices on either side are different. You might have the first two steps the same, but in the last step it wouldn't be rotating by the same amount of theta, but it could be a different angle phi. SVD is also possible, mapping a particular dimension into either a higher or a lower dimension. What this means, X transpose A equal to Y. By just looking at the dimensions, you see that you get a row vector, and I would say that each element in this row represents a corresponding column in A, which is just the coordinate of that particular column in the direction of X. There was a tall columns in A, and I've reduced the size of the column into just a single object. This vector X moving in the 2D plane. I've taken a two-dimensional object, the point here, and I put them on this line. So now all these points can be just represented by the lengths from the origin on this line.
Let's look at a real-world application of reducing dimensions. I have a medical data set, matrix A, rows representing patients, and columns, the attributes of tumor like cell size, cell shape, clot thickness, etc. The following code generates a plot which is obtained by plotting coordinates of each patient with respect to the highest singular vector of matrix A. The plot shows it's possible to reliably discriminate between benign and malignant samples. Hence, SVD produces separated features or coordinates that can facilitate the classification objective.
The broad picture, it's just for fun. Dude, you shouldn't sit there, man.
Was it U or V?